In this lesson, we're going to discuss the location of relative extrema. So we're going to discuss a theorem that describes a property that all relative extrema exhibit. And this theorem will help us to develop a technique to locate relative and absolute extrema. Now let's start by considering the graph of this function. So we have a piecewise defined function here. And here's what its graph looks like. Now this is over the interval from -2 to 4. And notice that we have relative extrema here at -1, 7 and down here at 1, -13. This is a relative maximum and this is a relative minimum. It also happens to be an absolute minimum over the interval from -2 to 4. Now you notice something special about these 2 points, and this is why we point them out. This point right here, you have a horizontal tangent line. And so what that means is that the derivative at this point is equal to 0. So we see that f prime of -1 is equal to 0. At this point down here where we have a relative minimum, our derivative does not exist because we have a cusp at that point. So you notice that f prime of 1 does not exist. So what this indicates is that when we have relative extrema, that it seems like either the derivative should equal 0 or the derivative may not exist. And so where the derivative is equal to 0 or does not exist for a function, those are special points that we need to consider when we're trying to find relative extrema. So that leads us to the next definition. So this is our definition for critical numbers. So we let f of x be defined at a point C. Then if f prime of c is equal to 0, or it does not exist, then we call c a critical number for the function f of x. Now the following theorem gives a relationship between relative extrema and critical numbers. So this theorem states that if a function f of x has a relative maximum or a relative minimum at x equaling c, then c is a critical number of f of x. Or in other words, then f prime of c is equal to 0 or f prime of c does not exist. That's what the critical number means, right? So if the function has a relative maximum or minimum at c, then f prime of c is equal to 0 or f prime of c does not exist. In other words, c is a critical number. That's a very important theorem because that's going to help us to develop a technique to find relative extrema. Now let's take a look at the proof of this. So we're going to use the alternative definition for the derivative. That is that f prime of c equals the limit as x approaches c of f of x minus f of c divided by x minus c. Remember, the definition we normally use is our limit as delta x approaches 0 definition, but this is the same as this definition down here. We would just have to let the c plus delta x right here, that's just our x. Okay, and this part right here would be x minus c if we let x equal c plus delta x. Okay, now let's start our proof. So we have to assume now we're going to assume f of x has a relative maximum. The proof of the relative minimum case is exactly the same as what we're going to go over. So we're going to assume f of x has a relative maximum We're going to assume f of x has a relative maximum at x equaling c, and we want to show either f prime of c is equal to 0 or it does not exist. Now we have two cases. If f of x has a relative maximum at x equaling c, then either so if you're given a function, then really this is true at any point. Either your derivative is going to exist at that point or it's not going to exist. So let's look at two cases. The first case, the easy case, is if it does not exist. So case 1, if f prime of c does not exist, well then we're finished, because that's what we wanted to show. We want to show either f prime of c is equal to 0 or it does not exist. So if it does not exist, we're finished. So then we're finished. Okay, so that part of the proof is easy. Now case 2, suppose f prime of c exists. Well, we need to show that the derivative is equal to 0 then. So we want to show now, let's go back to our limit definition up here, and let's also note this. If we're assuming f of x has a relative maximum at x equaling c, then what that means is that f of x is less than or equal to f of c for all x in a neighborhood of c. We'll say all x near c, right? So now let's look at the limit definition. So f prime of c, well, we're going to look at the left and right hand limits. So let's consider the left hand limit first. Right, now if we look at the left hand limit here, well, we know that this part right here, that is going to be negative. Because if x is approaching c from the left, that means x is smaller than c, so x minus c will be a negative number. And the top, the numerator, well, f of x is always less than f of c, so this is going to be less than or equal to 0. So we have a number less than or equal to 0 divided by a negative number, a number that's less than 0. So this number is going to be greater than or equal to 0. Right? We're going to have a negative divided by a negative, so this will be a positive number. So our left-hand limit is going to be positive. Now let's look at the right-hand limit. I'm going to move over here. If we look at now if we're looking at the limit as x approaches c from the right, the denominator here is going to be greater than 0 because x is larger than c. The top, the numerator, is still going to be less than or equal to 0 because c is where f has a relative maximum. And so this quantity, you're going to have a negative number divided by a positive number. This is going to be less than or equal to 0. All right, now we know that the derivative exists. We're assuming the derivative exists. So we know that the limit as x approaches c of exists, right? We're given that. We're assuming that. And so what that means is that the left and right hand limits must exist and be equal. However, the left hand limit is a positive number. Well, it's greater than or equal to 0. The right hand limit is less than or equal to 0. The only way these two limits right here can equal each other, the only way these two limits right here can equal each other is if they're both equal to 0. That's the only way. So therefore, this must equal 0. And we're finished. All right, so that concludes this proof. And let's note one other thing here about this. Now let's note one other thing about this theorem before we leave. The theorem only works in one direction. That is to say, it makes the statement, if f has a relative max or minimum at c, then c is a critical number. But it doesn't go backwards. It does not say, if c is a critical number, then the function has a relative maximum or minimum at c. It does not make that statement. And you can easily see why that's true. For example, if you just consider the graph of a function that looks like this, right here at that point, c, as I have it drawn, c is a critical number. F prime of c is equal to 0. But as we see here, this point is neither a relative maximum nor a relative minimum. So we cannot make the statement that if c is a critical number, then f has a relative maximum or minimum at c. That is not true. So this theorem only goes in one direction. If f has a relative maximum or minimum, then you have a critical number.